right, scholars, I am excited. We're going to practice learning to take lessons from videos because, like, I'm ever gone and stuff. This is how you're going to take your notes. One thing I want you guys to get used to is when you have an off-campus learning day or a snow day or something like that, I will always probably give you notes unless there's a certain worksheet I want to do. So here's the thing. On Monday, all you have to do is lesson 1.7 homework. The notes, which you're going to fill in, which are, quote, due on Monday, so that way you can do the homework on Monday. I'm just going to look at the paper copies in class so we can do on Tuesday as well. So I'll basically, you can get 2 grades in 1 on here. So today we're going to be working with probability. Now we're going to use a lot of different terms and stuff when we are working with this, but I first want you to watch this video about scamming people. Let's see if I can get it. I don't think it's going to come in big. Is it going to let me get bigger? Nope, full screen's not available. All right, let's try this. We're going to go to a link instead. All right, here we go.
11 feet. 11 feet. It's no secret that carnivals exist to make money. And to do that most effectively, they employ a bunch of little tricks to make you overestimate your chances of winning, in some cases to such an extent that it's basically a scam. So I spent a couple days coming out to this amusement park and observing and collecting data on all of the carnival games. So today I'm going to tell you which games are the biggest ripoffs and the scientific reasons why. I even Nancy Drewed how much the carnival actually pays for the prizes that people can win. But there is hope, because I'll also show you some legitimate tricks on how to win the most popular games, along with what happens when you show up to the carnival with your professional baseball playing buddy who happens to play for the New York Mets. Let's get started. You can sell this $5 spatula on Amazon.
Of course, we have to go through the commercial. Skip.
Any kind of legitimate investigation needs to start with solid data as the foundation. So with the promise of unlimited churros, I had some friends secretly help me collect data on all 24 carnival games for a full day. Not only did we capture how many times each game was played, but we also recorded how many times people actually won each game and the prize they won. And so the first observation, based on the data we collected, is that this relatively small park collects $20,000 a day off their carnival games alone. So to help frame the rest of the observations, we'll divide the games into 3 groups. The first group, you've got the random chance games. Games like these, where no skill is involved and you're basically just rolling dice. And for the second group, you have your skill-based games like the basketball shot or the milk bottle throw or the basket toss game, where if you bring some kind of skill or strategy to the table, you can increase your chances of winning. And the final category are the games that are pretty much impossible. These ones are borderline scams. There are 3 games in this category that lots of people attempted and nobody won. And if they did win, like in the case of the ladder climb, it was for a very specific reason, which I will address later. So let's start by talking about the random chance games. Calculating your chance of winning here is pretty straightforward. You just divide the winning outcomes by the total outcomes and you get a percentage. So in this case, there are about 1,600 total cups and 160 winning cups. So that's a 10% chance, or 1 in 10 throws will win. There are a ton of games similar to this, but the catch is they always use balls that are lightweight and have a high coefficient of restitution, meaning they bounce really well off things. This makes it much less likely the ball will end up where you originally aimed it. To illustrate this point, think how much easier this game would be with beanbags, which are heavier and don't bounce. With a ping pong ball, however, any imperfection in the aim of your original throw is magnified, which essentially randomizes things. If you have no skills, these are the games that you want to play. But don't get too excited, because even when you win, you lose. After some investigative work, I uncovered the source where they ordered their prizes from, and so even if you got lucky and won on your first throw, it would cost you $1.50 for a prize that cost them 45 cents. But you usually don't get it on your first try, so treating this as an expected value problem in statistics, it would take you an average of 5 times to land it in a yellow cup, which means you pay $7.50 for something that cost them 45 cents. In the case of the big prize, by landing it in the super rare gold cup, it's even worse. It would take you an average of 25 tries, which works out to $38 for something that cost them $6. And I'll add, the number of people we observed winning matched up pretty well with these statistical predictions. Now let's talk about the second group, which are the skill-based games. And one of the most popular in this category is the basketball toss, with 825 plays the day that we observed. Now a standard three-pointer is 24 feet back on a rim that is 10 feet off the ground. But in this case, the line is 28 feet back on a rim that is 11 feet off the ground, which is subtle, but if you have a deadly three-pointer locked into your muscle memory, you will tend to miss short, which is exactly what we saw a bunch. The reason they have the big slope tarp in front is so that someone can't stand directly underneath the rim, where the height difference would be much more apparent. And here again, even if you go Steph Curry and drain your first $3 shot, you still lose because they only paid 80 cents for that basketball. Here's another example of getting you to overestimate your chances of winning by making subtle changes, because the table is slanted up slightly, which will reduce the horizontal velocity of the ball after the bounce. So even if you dominated this game all through college, your previous experience almost becomes a handicap. This measure your pitch speed game is borderline fraudulent, as their radar gun registers about 15 miles an hour too slow. And I know this because I measured the distance and then recorded it in high speed and counted the frames. This pitch was clocked at 69 miles per hour, but it's much closer to 84. For the milk bottle game, the only catch here is the bottles are metal and therefore heavier and more stable and harder to knock down than a typical bottle of that size. I've seen some carnivals though where these are bottom weighted, which would make them more steady and thus less likely to tip. To figure out which kind you have, you can ask to hold it, and the point at which it balances on your finger is the center of mass. The key to winning this game is hitting them right here with a hard enough throw to introduce sufficient kinetic energy. But don't throw it too hard, because we notice those who threw their hardest usually sacrificed on accuracy. About 1 in 14 people knock this over on their first try. And then finally we have the basket toss game, and the key here is to have your first bounce hit on this front lip to reduce the kinetic energy enough that it won't bounce back out. About 1 in 10 throws will win on this game, according to our observations. And now this brings us to the final category of the near impossible games, and there are 3 of them. On this first one, the goal is to shoot out this red star completely with this automatic BB gun. So the best strategy is to basically shoot a circle around the star to cut it out. Not only are the guns not accurate or precise, but the bigger issue is that you start out doing really well because there's enough surrounding paper for the BB to easily rip through like this. But Newton's third law tells us that you can only push on something as hard as it can resist your push. So at the end you have these barely supported pieces of the star that just move out of the way when the BB comes without building up enough stress to rip the paper. Out of 120 plays, we saw nobody win this game all day. This ring bottle game is also impossibly difficult. Again, it's a lightweight object that's really bouncy to encourage randomness, but the actual inner diameter of the ring is really close to the outer diameter of the bottle. This means that any throw besides this pretty much perfect one will send the ring bouncing away without settling in on the bottle. If you really want this bear, I suggest going on Amazon and getting it for $47. I literally can't tell you how much money this will save you, because of the 840 rings we saw thrown, none stayed on the bottle. Which brings up sort of an obvious rule of thumb. If you want the feeling of winning a game, do not stop at any booth that offers really big prizes. And for the final near impossible game, let me reiterate that as a carnival owner, the most lucrative games are those which the customers overestimate their chances of success. No game is a better example of that than the ladder climb. There's a subtle issue with this game that I think people realize but don't internalize the significance. The ladder converges to be supported on the wall at 1 point instead of 2. If it was attached at 2 points, it's like crawling across a rope bridge, which is pretty easy. Let's pretend this is you, and if you shrunk all the weight of your body down to the average location, we call that spot the center of mass, which we'll mark with this dot. And once again, we can double check this is the right spot because it balances perfectly on one finger. If you draw imaginary lines connecting the different support points, that creates an area, and as long as your center of mass dot is within that area, it's impossible to fall off. But as soon as your center of mass dot is even a little bit outside of the area of supports, you start to rotate and fall off. And this is true no matter which way you orient it. If you've ever bent over to pick something up, you actually know this fact, whether you realize it or not. In this case, the region of support is between the back of your heels and the tips of your toes. When you reach over, you will naturally move your butt back to keep your center of mass in between those support points. And if you don't believe me, try picking something up while standing against the wall so you can't move your butt back. At the very moment your center of mass gets beyond your toes, you start to tip over. In the case of the ladder game, you're only connected at one point, so even though it looks wide because the ladder runs, that area of support reduces down to a line. So if you don't keep your center of mass directly above that line, you will start to rotate and fall off. In other words, to win this game, you basically need to be able to crawl across a tightrope. And you might think, well, I can do a slackline, so I can do this. But a slackline is actually much easier for two reasons. You can flail your arms and legs out to adjust your center of mass to keep it directly above that line of support. And your center of mass is higher, increasing your mass moment of inertia, making you more stable. In the same way, it's easier to balance this umbrella when it's extended versus when it's collapsed. So while there are a few videos that say tricks like maintain 3 points of contact, they're all basically useless, because keeping your center of mass directly above a line is just something you have to get a feel for. That takes a lot of practice. But once you've had enough practice, this is the one game at the carnival that's basically all skill, so you can win every time and clean them out. Unfortunately, the carnival owners know this, which is why it's also the only game with this super lame caveat. So now that we were carnival experts, I called my buddy Matt Winokur, who was recently just drafted to play baseball for the New York Mets, to maximize our chances of winning any skill game that had to do with throwing. So clearly Matt had a deadly lock on any throwing game, but basketball is more my game. So to finish off the day, I decided I would bring his ego back into check. But as it turns out, if you are a world-class athlete in one sport, you are a really, really good athlete in all sports. So in conclusion, you should play the games if you think they're fun. Just know the odds are heavily stacked against you, so if you lose, it's NBD. Unlike this guy who lost his entire life savings playing carnival games. And if your motivation is to gain the love and admiration of someone special via a stuffed animal like this, you don't need carnival games to do that. Amazon works totally just as well. I just bought this for you, my lady.
So, as you can see, kind of funny, but the idea of probability and chance is actually something we do quite a bit. And I bet all of you at one time or other have been like on a carnival game or something in that manner. So, I mean, it kind of makes sense. So let's go through and answer these questions now that we've watched the video, okay? Here's the questions. What were the 3 categories of the games, okay? We had what were called the random chance games, right? We also had the skill-based games. And what was our last ones? The near impossible games. Okay, now I want you to think about what is an example of a random chance game and how do you calculate the probability of winning it? Okay, so the one that was a really easy one that we could all probably remember was the ping pong ball with the colored cups, right? When you work with it. So the ping pong ball with, by the way, that's just an abbreviation for with, colored cups. Okay, do you remember how we calculated it? We had to know all the possible winning outcomes. So it's the number of possible winning outcomes divided by the total number of outcomes, or the number of total outcomes. Okay, now, if you remember on this one, what were the values, okay? Well, the possible winning outcomes were the colored cups, and those were 160. Then we had the total number of outcomes, which was 1,600. Well, that reduces down to 1/10. And 1/10, if we convert it to a percent, is what percent? because a decimal is going to be 0.10, so that would be 10% would have been our probability of winning, or 1 out of 10. So every time that you would bounce a ping pong ball across it, you would have 1 in 10 chance of doing it. So basically, you'd almost have to play 10 times before you guarantee to probably have a win. Okay, so that's kind of the intro of probability. It was a fun one to do. But let's get down a lot of vocabulary. Hey, when we have vocabulary, put that in the back of your head. You know you're going to have questions on it for a quiz or a test. So first of all, my friends, I'm going to move something that's on my screen. I don't know if it's going to help me or not, but we're going to do it here. Probability. Well, probability is the chance or likelihood of an event occurring. For instance, what was the likelihood you were going to have a quiz on Friday? 100%, because Mrs. Gregerson doesn't lie about having quizzes, and I've taught enough years, I rarely ever change them. So that type of scenario. Now, how do we calculate it? And this I would highlight if I were you. It says probability is calculated as the ratio, which means a fraction, of the number of favorable outcomes and the number of total outcomes where all outcomes are equally likely. So remember, ratio means fraction. So here's how you do it. The number of favorable outcomes over the number of total outcomes. So we have to be able to know what are our possible total outcomes when we're working with it. Now, here's the thing. When we work with it, an example of this would be like a 6-sided dice, okay? Where on a 6-sided cube or dice, they're all equal size, and we know we have like 1, 6, 2, and that no matter what would be like, for instance, the probability, okay, of rolling a 1. So notice notation. We put a P for probability, and then we say what we're doing the probability of. So let's say roll a 1. Well, how many outcomes do I have on a piece of dice that has 6 sides? Remember, it's 6-sided dice. It would be 6. How many times can you roll a 1? A 1. So there'd be 1 out of 6 would be the possibility of rolling a 1 on a 6-sided piece of die. Now, you can write probability a couple different ways. You could do it as, my friends, a decimal. So 1/6, make sure I say the decimal correctly or I'm going to get in trouble here, is going to be the same thing as 0.1. And I would round after probably about 2 spots, be about 0.17. It's really 0.16 repeating, just so you know that. Or we could write it as a decimal. All of those are the same thing as showing the probabilities. We need to be able to think about it. Now, what are the outcomes of probability? Probability outcomes are always between 0 and 1, okay? Or you could say between 0 and 100%. To be 0, it's never going to happen. To be 1, it's a guaranteed going to happen, okay? Now, let's talk about how to find the probability of something very simple, like drawing a playing card from a deck of cards. Let's look at this one here. It says, what's the probability of drawing a heart card from a standard deck of cards? Okay, let's talk about a standard deck of cards, just so we are all on the same page. Not everyone plays card games and stuff, so let's make sure we have this. So first of all, a deck of cards is a total of 52 cards. All right? Now, you have what are called 4 suits. Okay, and those suits are the following. They're either a red suit or a black suit. So you either have hearts or you have diamonds, or you're going to have what we call clubs. So it looks something like this, or we'd have what's called spades. And they look kind of like a shovel, at the end of a shovel, like a spade is the kind of word we use for it. And for each and every one of these, you have 13 cards. Now, of those 13 cards, okay, there's some things you need to know. Each suit contains the following. We have what are called 3 face cards. 3 face cards, those are going to be the king, the queen, and the jack. They literally look like royalty if you look at how the cards are done. Notice we did not count the joker. The jokers don't count. That's different for other types of games. But then we have the following: ace through 10. All right. So the ace is what number? That's number 1. And so I'm going to actually put it here, the number 1 by ace. So we get the numbers 1 through 10. So that's 1 through 10. So that's 10 cards. And these just have numbers on it. All right. So we got pretty easy. So we got ace, 10. We have number cards. Now, we can do a lot of different ways of drawing this. So for instance, notice notation once again. If I want to have the probability that if I mix up the deck of cards well, I want the probability of drawing a heart. Okay, I just want to draw a heart. Well, what are the total number of outcomes? Well, what are the total number of cards? That's going to be 52. But how many hearts are in my deck of cards? That would be 13, which would be 1 out of 4. So that'd be 1/4. Now remember, we always have to simplify fractions. So the probability 1/4. Now we could also say that's 0.25, or we could call it what? 25%. All right. So that would be just an example of simple probability. Notice notation. If I'm looking for probability, I put a P there and I put a parenthesis about what I'm looking the probability for. Now, there's some other words that you need to know that are commonly used. The first one is chance. We use the word chance or likelihood the same way. They're often used synonymously, which means they're used the same, and refer to probability of an event. So the chance that something happens or the likelihood that something's going to happen is this value. However, this is a new one for most people. This is where like gamblers love doing this, okay? So not that I do not encourage gambling. In fact, I think it's wrong, so don't do it. But the fact is we have a word that's called odds, okay? Now, I want to know the odds. Now, this is very nuancey, so please watch carefully. The odds is the following: a ratio, so it's a fraction, of the number of ways an event can occur to the number of ways an event cannot occur. Whoa. And then to write this, we use a colon instead of a fraction bar. So here's the idea again. The number of ways an event can happen to, and then we use that as just ratio notation, the number of ways it cannot happen, okay? And I'm going to show you a simple little example of this. All right. So it says, what are the odds of drawing a heart from a deck of cards? Okay, so just think about this carefully. That is the number of ways it can, an event, I should say an event can happen to the number of ways it can't. Now, I want you to be really careful with this. How many hearts are in a deck of cards? 13. So that's the number of ways it can happen. Now, how many ways can it not happen? Here's where it is. Well, that's all of my events minus the 13 that can. So now that became 13 to 39. Now, here's the deal. I've got to simplify it. So in my brain, I think of this as 13 over 39. And what is it reduced to? 1/3. So my odds of drawing a heart is 1, 2, 3. And we read it 1, 2, 3. Okay, so that's odds. This is homework type questions. So make sure you're really paying careful attention to this and keep your notes and get your notes done before you do your homework. All right, some more terms we need to know. We also have what's called a trial. Okay, a trial refers to a procedure that can be repeated and usually reserved for experimentation or simulation, in which the experimenter adjusts a factor in anticipating of some result. The result of any trial is an outcome. Now, let me give you a simple idea of a trial. Flipping a coin is a trial. We know the outcome is going to be heads or tails. So when we flip the coin, we're trying it to see what we get. Okay? Now, when flipping a coin, what is the trial and what is the outcome? The trial, okay, is flipping the actual coin. The outcome is getting a heads or tails with that coin. All right, so it's some terms. So we have a trial is like an experiment, something like that, or a simulation or practicing something to see what would happen, testing it. An outcome is just what we get as a result of doing the trial. All right, now there's another thing. We have another word that we need to know. We have what's called an event, okay? An event is in a collection of outcomes, all right? So here's an example of what we mean, okay? It says, what are the outcomes of the event of rolling an odd number with a standard number cube? Okay, a few things you need to remember. Remember a standard number cube. All right, all's going to work here. We got 1, 2, 3, goes all of the different sides. All right, so what are the actual values? Okay, we know that the outcomes are 1, 2, 3, 4, 5, and 6 if you roll a number thing. But what did it ask for? What are the outcomes of the event of rolling what we got here? An odd number. Well, what are my odd numbers? 1, 3, and 5. So my outcomes are 1, 3, and 5, which are my odd numbers that I could roll. Now, where did I get the 1 and 3 and 5 from? It is called the sample space. The sample space is the set of all possible outcomes. Guys, this is huge. Boom. Sample space is the set of all possible outcomes. So what did we actually do? We wrote earlier, without really meaning to, the sample space. Let me click on this so it will quit moving on me. So what is the sample space if you roll a die? I could roll a 1, I could roll a 2, a 3, a 4, a 5, or a 6, because a standard number cube has 6 sides. Okay, that's huge. All right, here's another term you have to know. So notice a lot of this is just tons and tons of terms. All right, first thing, what we know, random. Or if something's random, there's no bias. That means you can't really control it. It just happens. You have no control with this. So that's random. We love random things. We don't want it to be a controlled bias. So when you roll a number on a dice, it is a random roll because you just roll it and then you see what you get. Like you have no control of what it's going to do. All right, the next outcome of a random event is not known. That means, like, if I roll a dice once and I get a 1, I don't know what I'm going to roll for the next one. It's still a free chance of getting the roll. But over repeated trials, the proportions of specific outcomes could be predictable, right? Here's an example. What do we know? What is a fair game? A fair game is one which you expect to win as often as you expect to lose. Kind of like the idea of flipping a coin. If you get the probability of a heads or probability of a tails, you know you're going to either get a heads or a tails. If I always pick heads, I would expect sometimes that the coin, when I flip it, would give me tails. All right, another one. This one is used a lot in this world. This is called theoretical probability. Think of it like this. Theoretical probability. Theater is not always reality, but it's acting out. Sometimes it could be considered reality. Theoretical means it is calculated on reasoning about an event without doing any trials. Like I'm not physically doing it, I'm thinking about it. Like for instance, the probability of rolling a 1 on a standard cube is 1 out of 6. Why? Because I know there's 1 out of 6 possible outcomes. But I need to actually roll the die in order to figure out what it is. Now, we also have another term. It's called experimental probability. It's results of a what? An experiment. What do we do with experiments? We do trials of something to see what happens. Okay, so here's the thing you need to know. This hopefully will be a little bit better. Here's an example. The theoretical, if I can spell theoretical all of a sudden, guys, here we go. Probability of getting heads in a coin toss is 1/2. But if I tried this 10 times, I could get an experimental probability of getting a heads out of 10 trials, 7 out of 10. Does that kind of make sense? Okay, now I want you guys to look at the next one. We're going to look at finding the probability for another carnival game. All right, we're going to do a dartboard. All right, so this is a square dartboard. So let's read the rules. I said the dart game at the carnival has the following rules. You pay $2 for each dart. You are then blindfolded and instructed to throw the dart at the wooden board that is painted to look like the following image. If the dart lands on a yellow square, you receive $4. But if it lands in the blue area, you lose your $2. If your dart misses the wooden board entirely, you get another chance. The yellow area is 1/4 of the total area, and the blue area is 3/4 of the total area. Is the game favorable to the player? Let's see about this. All right. First of all, what does your instinct say? If I was to throw this dart, and let's just say I even know that I'm hitting it, right? Is it favorable for me? Is there a chance that I'm going to actually win $4? What do you really think in your head? You're thinking like, hey, 3/4 of it's blue. Not a good chance for me. So let's talk about what this means. Now, let's talk about notation. So this is notation. When we're being in general, the probability of an event, this is the notation. It means the probability of whatever, and this is when you make it specific, is going to occur. So let's have a little bit of fun and see if we can do this. When I say here, the probability of blue, that's the probability that the dart thrown at the board hits the blue region. Well, how much of the area is blue? That's right. It's 3/4. If we don't say 3/4, what would be the percent we'd say for this? 75%. Okay, blue, you don't get your money. What do we have to hit? Yellow. So what's the probability of yellow? This reads the probability that darts thrown at the board hits a yellow region. So the probability of hitting yellow is how much? 1/4. Guys, or we can say that is what? 25%. Here's the thing you need to know. It's not favorable towards you. 75% of the time, you are supposed to be expected to hit what value? Blue. Basically, would this be one of those games you would have to practice in order to make it favorable for an outcome? Yes. Okay, now I'm going to do something I normally don't do. I'm actually going to kind of set you up for homework success on Monday for off-campus learning day. All right, so when we look at the homework, this would be one of those times that if I were you, I'd look at previous lessons and maybe rewatch this portion of the video on Monday. The first thing you need to know, problems 1, 2, and 3 are basically review from lesson 1.6, okay? Lesson 1.6 was due on Friday, and this is the idea of the normal curve. So remember the 68, 95, 99.7 rule, so the empirical rule. So this is helping you figure out the empirical rule. Are you guys with me on that? Use what? The empirical rule. And that's the one that we learned on empirical, I can spell, guys, rule. All right, now I want to do 3 problems with you because people aren't always sure of this and people don't know how to get this. Okay, this is saying finding the odds of, make sure I do this again. I'm going to set picture as background. All right, the odds of an event given the probability of the event. So this is a probability of an event going to happen. So remember, this means what I want. So this is the favorable outcomes over the total outcomes. However, I want the odds of this. The odds is remember, what's the odds? This is going to be the favorable total to the what? Unfavorable. But now, how do I know what my unfavorable total is? Well, it's just the total minus what is good. So the total for this is going to end up being 3. That's the favorable outcomes. But the unfavorable outcomes is the total minus the favorable outcomes. So my ratio is going to be 3 to 4. So my odds are 3 to 4. Does that kind of make sense with this? Okay, now let's do another one. Now we're going to go backwards on this one. What's the probability of an event occurring given the odds? So remember, this is favorable and this is unfavorable. So the key thing to know is how many total outcomes are there possible? Well, the total outcomes possible is 10 plus 1. The unfavorable and the favorable. And then what do we put on the top? The favorable values. So that is going to be 10 to 11. Or could we write it like this? 10 to 11 is the value. Okay? Now you need to do the examples. You also need to do B, C, D, B, C, D. This is not choose A, B, C, or D for your answer. There's nothing to choose. I want you to find the odds for A, B, C, and D, and I want you to find the probability of the event occurring for A, B, C, and D. Okay. Now, one more thing. The key with finding probability is knowing total outcomes. So I want you to look next over here. So it's using the chart that shows the class and gender statistics for the students taking an Algebra 1 or Algebra 2 class at La Mesa High School. If a student is taking an Algebra 1 or Algebra 2 course is selected at random, find each probability. Expressed as decimals, rounded to the nearest thousandths. So your answer has to be the way that's being requested. Now, here's the thing. You can't find probability unless you know the total. So the key thing we have to know before we can do anything is to know the total. Well, how do I find the total? Well, friends, you add all the total students together. So let's do that real quick. I'm going to do it on my calculator. So guys, if I add together wrong, that's my fault. You can fix it on your homework. So we get, all right, 95 plus 101 plus 154 plus 145 plus 100 plus 102. All right, so the total number of students I have is 693. So that's the total possible. You can think of it as your sampling set, your sampling space. I have 693 students in my sample space. I want to know the probability that the student, if I was to pick them random out of this, probably, we made some sort of survey or whatever, is a sophomore who is a female student. How would I find that? Well, I still need to know the probability of my students. So that's 693. But then I look over here and I'm looking for sophomore females. How many sophomore females are there? 145. Now I let the calculator do the work and I just go 145 divided by 693. What does that gives us? That gives us 0.20, and I'm running around to the nearest thousandths. That's 3 decimals, by the way, places. And that would be the probability of being a sophomore female. Okay, I'm not going to do any more on this homework. This is what's going to happen for Monday. So Monday, your job, or you can do it over the weekend if you want to do it earlier, is to make sure you finish your notes, but then to please go ahead and do your lesson 1.7 homework. If you want to work ahead instead of doing it on Monday, no problem with me. All right, great job, guys. I'm thankful for you listening and doing this well.